Okay, so the next thing that we can do with induction is we can try and prove divisibility. We're going to use exactly the same technique. We're going to use our base case, our assumption, our induction, and our conclusion. But the things that you're proving are sometimes a little bit more unintuitive. So we're going to look through three examples here. We're going to start with 3 to the 2n plus 11 is divisible by 4 as our statement that we're trying to prove. Once again, we start with the base case. So if n equals 1, then this gives us 3 squared plus 11, which is 9 plus 11, which is 20, which is 4 times 5. So yep, base case is true. That is definitely divisible by 4. After that, we want to go to our assumption. So we're going to assume this is true for n equals k. In that case, we would get 3 to the 2k plus 11, and then this is where it's different from when we were doing the series. This is not equal to anything specific, it's just it's divisible by 4. Now, how do you write that? Well, you say that it's equal to 4, let's pick a letter we haven't used there. Let's say it's equal to 4m. Okay, that's our assumption. We then want to go to our induction step. So we want to show it's true for n equals k plus 1. So how would we do that? Well, we want to look at what the term would be for n equals k plus 1. We would have 3 to the power of 2 brackets k plus 1 plus 11. Now, what we want to do is to try and put that in terms of the thing that we've just said is true. So how can we do that? Well, we can use some index rules on that left-hand side. Certainly we'd expand that bracket to get 3 to the 2k plus 2 plus 11. And then we'd think, well, what we want this to look like is 3 to the 2k plus 11. How can we do that? Well, we could use index rules to split this up into being 3 to the 2k times 3 to the 2. What next? Well, 3 squared is 9. So this is equal to 9 lots of 3 to the 2k plus 11. That's almost good, but we kind of need it to look like this. We need it to look like 3 to the 2k plus 11. How can we do that? Well, we could say that this is equal to 9 lots of 3 to the 2k plus 11 minus 11 plus 11. So all I've done is I've sort of added and took away 11 from that 3 to the 2k, so obviously this thing in the bracket is exactly the same as what we had, but now it's closer to the form that we want it to be in. We can then expand this bracket. We can say we've got 3 to the 2k plus 11, and then 9 times that 11 will give us a minus 99, and we've still got our plus 11. So overall, 3 to the 2k plus 11 minus 88. And we just need to show that this is a multiple of 4. So how can we do that? Well, we know from earlier that 3 to the 2k plus 11 is equal to 4m. So this is equal to 9 lots of 4m minus 88. And remember, we're trying to show this is divisible by 4, so we can take a factor of 4 out here. We can say this is 4 lots of 9m minus 4 lots of 22. So overall we have 4 lots of 9m minus 22. Therefore, divisible by 4. Don't forget, you would obviously need your fourth step here. So we'd need to say statement is true for n equals 1, and assuming true for n equals k implies true for n equals k plus 1, therefore true for all n in the naturals. Cool, so that's the general idea, and you can see it's a little bit more fiddly than what we did with series. You've got to rearrange the stuff a lot more carefully. Okay, Let's have a look at another example. So we want to show that n cubed minus 7n plus 9 is divisible by 3. It will surprise no one to know that we're going to do n equals 1 to start with. So that would give us 1 cubed minus 7 times 1 plus 9, which is 1 minus 7 plus 9, which is 3, which is definitely divisible by 3. That's equal to 3 times 1. Okay, so we want to assume true for n equals k. So if it was true, then k cubed minus 7k plus 9 would be equal to 3m, whatever 3m actually is. We're then going to try and show it's true for n equals k plus 1, and so that would give us that we will have k plus 1 cubed minus 7k, oh, not minus 7k, but minus 7 lots of k plus 1 plus 9, and then again we're trying to pull out this in some form. So how are we going to do that? Well, I think we might actually need to expand this. Yeah, because we're trying to get just a k cubed on its own, and that's only going to come out of expanding this bracket. So, apologies. K plus 1 cubed, let's do it over on the side, I think. Yeah, it would be k plus 1 times k plus 1 times k plus 1. So, generally a good idea to expand the first two brackets, and then to simplify. So if I times it by k, I get that. If I times it by 1, I get that. Bring that all together, gives us k cubed plus 3k squared plus 3k plus 1. Okay, cool. So I can put that in. So we have k cubed plus 3k squared plus 3k plus 1 minus 7k minus 7 plus 9. Okay, let's collect terms. K cubed plus 3k squared plus, no, minus 4k, and then plus 3. And we're trying to show this is something to do with k cubed minus 7k plus 9, aren't we? So let's take that out. So we could then split this up into being k cubed minus 7k plus 9. And then what's left over? Well, we'd also have a plus 3k squared. And then we actually had minus 4k, so we'd need to add another 3k. And then we actually had a plus 3, so we'd need to take away 6. Hopefully you can see where this is going. So what we've got there is we've got k cubed minus 7k plus 9, which is 3m. And we've also got 3 lots of k squared plus k minus 2. So overall, this is equal to 3 lots of m plus k squared plus k minus 2. So therefore it's divisible by 3. To be honest, that one wasn't too bad. We would then end with our statement, which I am not going to write out again. Cool. And then let's look at this beast. So we are trying to show here that 11 to the n plus 1 plus 12 to the 2n minus 1 is divisible by 133. Okay, you know what we're going to do. We're going to start with n equals 1. We're then going to try to assume true for n equals k, and we're going to hopefully show it's true for n equals k plus 1. So that would give us, base case would be 11 squared plus 12 to the power of 1, which is 121 plus 12, which is 133. So that's definitely divisible by 133. Yeah. Okay, we're going to assume it's true for n equals k. So that would tell us that 11 to the k plus 1 plus 12 to the 2k minus 1 is equal to 133m of some sort. Then we're going to try and show it's true for n equals k plus 1. So that would be 11 to the k plus 2 plus 12. So this would be 2 lots of k plus 1. So that's 2k plus 2. Take away 1, so that's 12 to the 2k plus 1. And then we need to try and put this in terms of something that we've already got. So let's try and split these up so it's the right powers at least. Let's go to this being 11 lots of 11 to the k plus 1. And it would actually be 12 squared lots of 12 to the 2k minus 1, wouldn't it? Because we've got to take 2 off the power. So we can expand that. We can say we've got 11 lots of 11 to the k plus 1 plus 144 lots of 12 to the 2k minus 1. Okay. What do we want to do with that? Well, I think we can try and take out a common factor of some sort. And the way we're going to do it is this. We're going to say that we've got 11 lots of 11 to the k plus 1 plus 11 lots of 12 to the 2k minus 1 plus 133 lots of 12 to the 2k minus 1. Why did I do that? Well, that means I can do this. I can say I've got 11 lots of 11 to the k plus 1 plus 12 to the 2k minus 1. And I've got 133 lots of 12 to the 2k minus 1. And what have we got? Well, we have got here exactly what we had here. No, not there even. Exactly what we had here. And we know that's equal to 133m. So hopefully you can see where this is going. This is going to be 11 lots of 133m plus 133 lots of something. So we can take out that common factor of 133 now. We can say we've got 11m plus 12 to the 2k minus 1. And I can say therefore that's divisible by 133. And then we'd end with our statement. Cool, so that's 3 examples of divisibility. You can see that it's all about manipulating index rules and trying to bunch things together so that in terms of our assumption. Cheers.